Utilizing the USART on the ATmega 328PB involves selecting various modes in order to receive the performance that you expect. To do so, you have to manipulate bits in its registers, including those in its baud rate register and its control and status registers. Specifically, if you wanted to control the baud rate, you would have to look to the USART baud rate registers, which are the low and high registers that decide what the baud rate, the bits per second of the USART will be. In this case, you can use these formulas depending on the speed that you are using. In our case, we are using the asynchronous double speed mode, so you could use these formulas to calculate the baud rate register value that you should enter. But for all intents and purposes, this table, provided in 24-9, is effectively the same thing because we have an 8 megahertz onboard clock, and because we are doing asynchronous double speed, the frequency oscillation is approximately 16 megahertz, which is why we can utilize this table. As such, if we wanted a baud rate of 9,600, we could utilize the given UBRR, which is the baud rate register value, of 103. And you can do that for various different baud rates. But having that baud rate, or one of these baud rates, in the actual register itself is what manipulates the baud rate itself. Now, for the number of data bits, the parity, and the number of stop bits, those are all found and reliant on bits in the UCSR0C, which is the control and status register C for the USART. As such, it can be seen that the parity mode is dependent on bits 4 and 5, where it follows the table 24-11, such that if you wanted the parity to be disabled, you would have 0, 0, all the way through to odd parity enabled at 1, 1. Furthermore, the number of stop bits is dependent on bit 3 in the control and status register C, where that bit being 0 means there's 1 stop bit, and it being 1 means there are 2 stop bits. Finally, in conjunction with a bit from control and status register B for the USART, the bits 1 and 2 of control and status register C are used to decipher what character size you want to use. As such, we can look to our program where initially, if we were to run it, initially our 103, which is our baud rate, is loaded into our UBRR register, which achieves that baud rate of 9,600 that we expect. And then, furthermore, we have a 6 in decimal that we load into R16 and then into the control and status register C, which, according to our table here, will mean that everything is 0 except for 2 and 1. And because of that, we have 0, 0. So we have asynchronous USART. And we have we have a disabled parity mode. We have a 1 stop bit, and because we have a 0 in our status register B, then we have 1, 1 for bits 1 and 2, meaning we have an 8-bit character size. So we have a baud rate of 9,600, 8 data bits, no parity, and 1 stop bit. So now if we open something like TerraTerm and have our COM3 port, we can run this program. And eventually it will load and work as expected. And that is because in our setup and our serial port, our USART is configured correctly, because all of this data here matches what's in the program itself. Now, as a result, we are able to do things like press L and use our menu properly, and press any other key to return back to the menu, and the program works as intended. Now, if we wanted to adjust the USART with the USART command, that involves going to our command here, selecting U, which is just another case, and then it calls the USART function. Now this sets two global variables that are also in the assembly program that enable communication between the two, and it sets them to 0 each. And now it requests a desired baud rate from the user, and it gives several options and switch cases for that. And then it stores the expected UBRR value associated with that into BR data, which is baud rate data. And by default, it is the 103, which gives us that 9,600 baud rate. And then it asks for the number of bits from the user. And so it can ask for, or the user can ask for 5, 6, 7, or 8. And based on that, it merely adds 2 times, because in this case the character size are in bits 1 and 2, so we want to skip past bit 0, so we go straight to bit 1. So we go to 2 times 0, 1, 2, or 3, because in this table we see that 0 is associated with 5, 1 is 6, 2 is 7, and 3 is 8, and that is true here as well. And by default you get that 8 value. And then you add that to the control and status register data, and you continue, requesting a desired parity mode from the user. And based on the parity mode that they select, which again is here, so for 0 it's disabled, for 1 it's reserved, for 1, 0 it's enabled, for 1, 1 it's enabled with odd, with 1, 0 it's even. And in that case, the default is 0, so it is no parity by default. It then requests the number of stop bits from the user, and in this case there's only 1 or 2 because it's a single bit, and by default it is just 1. And then afterwards it calls the UART update, which is an assembly label, and so it goes to the UART update here, and it says, okay, we'll clear everything that's currently in the USART, turn it off so that it is no longer attempting to receive or output data. It loads 0 to R17, loads the data that we got from the baud rate data to R16, and then writes it to the UBRR register. And as such, the baud rate data will change, and then it loads the control and status register data that we were adding together into R16, and then uploads it to the control and status register C for the USART. And that will effectively update the baud rate and the parity mode and the stop bits and the character size. And after that, it merely goes back, it returns. After turning USART back on, returns, and then it returns back to the command function. As such, if we open our tera term, whenever we do this, we can select U for USART, and it will show us our options for the baud rate. So for example, if we wanted to use a slower 4,800 bits per second, then we could select A. Let's say the desired number of data bits. Okay, well, let's say 7 instead of 8. Parity mode, I'm going to say even, and desired number of stop bits, 2 to be different. And after you do that, it seems like everything is going wrong. But that's because in our setup, our serial port no longer matches the actual USART information that we have in code. Therefore, we now need to adjust that and make it match. And so we selected 4,800, 7 bits, even parity, and 2 stop bits. And so when we apply that and then press anything, we can say, okay, well, that's an invalid command, but now we're back to our expected results in the code, even though we have changed the USART values directly. And as such, we can still do things like display our LCD and then press whatever button to return back to the menu. And as such, we have changed the values of the baud rate, number of data bits, parity, and number of stop bits while running the code.
So here we have our re-engineered ADC subroutine, which is reading a voltage from a thermistor and converting it to degrees Fahrenheit. So looking at the code, first we have the ADC underscore get, which is getting the HADC and LADC values to then be used to get the initial ACC value. And then we use this ACC value to adapt the thermistor to the ADC. And finally, we convert it to temperature by first converting it to Kelvin, then converting it to Celsius, and finally converting it to Fahrenheit. Once that is all done, we create a string to print the temperature to the command line. So if I pull up our command line, you will see the menu prompting the user to pick either L, A, or E. And if I click A, you will see that the command line prints the temperature in the room, which right now is 71 degrees Fahrenheit.
So now we're going to do the free running mode part of the demo. So here we have the same exact code for the Fahrenheit calculations, but this time it is set inside of a while loop just so that it keeps printing on the command line to the user. As you will see, this is a little bit of old code, so the ADC get is actually taken out of this loop because it has now been set in the status register. It is now set to free running mode so that it keeps getting that ADC value over and over again without being prompted. And as you can see in the command line, 71 degrees Fahrenheit is continuously printed to the user. And that value, if the temperature changes from the thermistor, it does change on the command line as the ADC is continuously getting a value. And as you can see, if any button is pressed, it immediately stops and brings back the menu.
And once again, we have the exact same code, except for one little line that changed. So when we go into the command line and we press A, it'll once again keep printing the temperature value, but this time it'll do it in a static position, so it'll stay on the same line that it was. And it also updates if the temperature changes in the room. And once again, if I click any button, I can immediately stop the loop and it'll print the menu.
For part 3 of our code, we're looking at the EEPROM. And so when we debug our code, I'll explain in the meantime. So we're taking in the first half of a data address. And so we take the first character of that from 0 to E or 0 to F, converting it to an integer value using the ASCII table, multiplying it by 16 since it's in the 16th place of the 2-digit hex number. And then we do the same thing for the second half, but instead of multiplying by 16, we multiply by 1. And then we add that to the first part to get the full integer address. And we add that to our global variable address L. And then address high is just the low plus 1. So here, let me show you. And so we can enter data 2, 3. And so the data currently there is P. And so now we can enter a new value. So let's just do M. And then from there, to prove that it works when you unplug the device and plug it back in, I'll unplug my microcontroller. As you can see, it's disconnected. Now I'll reconnect it. And start it again. And now we try it. So we can go to the same data address, so let's go 2, 3, and it's M in there, as I just entered. And with our assembly code editing the write and read programs, we added the address high and the address low instead of the predefined data address. And then I added the new data element, which is the value we're entering. And then for read, it just takes the value from that high and low address. For part 4 of our code, we're using the LCD to just scroll our team name. And so we set up our LCD, setting up all the display and the cursor movement and the shift direction. And then we're going to display our team name. And then we're going to loop through, checking for inputs and shifting the LCD display. So whenever I press L on the terminal, it will display it, and it will start scrolling. The best CSE 412 embedded systems group in the world. Group 9. And then it'll start scrolling itself over again. And whenever I press any key, it will stop scrolling. So I'm gonna press just a random letter, and there it stops. And it'll return back to the menu. And I can press L again, and it'll reset the scroll.
So you won't be here tomorrow?